So we had some fun rolling different objects down a ramp and seeing what different factors influenced how fast the objects went down the ramp. And ultimately what we found was that the object's rotational mass, or what we call the moment of inertia I, is what affects the rate at which it rolls. So what we'd like to do is couple this idea of rotational mass, rotational inertia, and use forces and torques using Newton's second law to predict the acceleration of the object down the ramp. There's another method to doing this, and we can use energy, just looking at a change in height of the object to calculate the final velocity of the object. The only downside to that method is that gives us only the velocity, and we'd have to take a second step after that using, for example, constant acceleration motion equations to work out its acceleration. And then finally, we'll take a look at some other problems that you'll go back and solve using some of these rotational concepts and rotational inertia and torques. So we ran a controlled experiment with the off to the races, the best we could at least. When you started out this process, you didn't really have any idea what was going to happen. But what we ended up with doing is finding out that we controlled certain variables along the way. So first of all, the ramp and the ramp angle did not change. The surfaces, I carefully chose all of our objects to have hard, smooth surfaces. For example, I have a foam ball that would have been nice to use, but the surface itself caused additional friction as it was rolling, and it threw off its results. And so I tried to get all the surfaces to be just hard surfaces against the ramp's hard surface. For mass, for example, what we did is we picked the 1-inch wooden ball versus the 1-inch steel ball. So they were the same type of objects, solid balls, and the only thing that varied was the mass of the objects. And then we ran experiments where the radius changed. For example, we took all 3 solid balls that were small, medium, and large sizes and saw what happened. And then we took a look at the thickness of the objects. For example, if I have a narrow slice of PVC versus a wide slice of PVC, does that affect how fast something rolls? And ultimately, we found that the mass, the radius, and the thickness did not matter, but the only thing that really did matter is, quote-unquote, our type of the object. And really, the key that brought this out is when we looked at 2 cylinders that were both 15 centimeters, but in one case, it was a brass ring. The masses were the same. But the mass on the brass ring was distributed way out to the edge, whereas the wooden cylinder was distributed evenly from the center all the way out to the edge. And we found that in this case, it was very easy to see that the wooden cylinder, even though it was identical in every other respect, beat the brass ring to the ground by a significant difference. So the conclusions we came up with was that if we have homogeneous object, for example, all the balls that we used are homogeneous, they were made and fabricated in such a way that they were uniformly, we could slice it in half and see a nice uniform distribution of its mass, either out at the outer edge or all the way through. So for example, if we had a thin-shelled hollow ball rolling down the ramp, regardless of its size or its mass, they all rolled down at the same rate. So mass or radius didn't seem to be driving the problem. And the only thing that really mattered was how the mass was distributed. The further out along the edge the mass was, the slower the object rolled. What do they have in common? Well, they all rolled, but otherwise they did not roll at the same rate. In fact, these two are brass ring and the solid wooden cylinder. Same mass, same radius, rolled down at quite different rates. And that was quite different from what we saw with these 2 solid balls, one of plastic, one of wood. Quite different masses, quite different radii, but they rolled at the same rate. And then we compared these 2, for example. We've got a solid wooden ball and a hollow ball, and once again we found that the wooden ball beat the hollow ball to the ground. And we found later on that was because all the mass was on the outside of this ball versus distributed throughout in this. The question is, what about our matchbox car? Do we treat that like a sliding object, or because it's on little round wheels, do we treat it as a rolling object? So these were all solid balls, and they all rolled down at the same rate. Radius and mass didn't matter. In this case, we found that our 2 solid cylinders rolled down at the same rate. The only thing I have to caution about was this is the only object that didn't have a hard, smooth surface, because this is rubber, but it did roll at the same rate, so that one worked out okay. Whereas these 2 guys were quite different from each other because all the mass is distributed out at the outer edge on this ring. Now, along with our Matchbox car, this is another object that's a good example of a non-homogeneous object. This is still a round object. It rolls quite well. But rather than having a constant distribution of mass throughout, we have basically several different pieces that have constant mass distributions. For example, we have the two large acrylic circles that each on their own would have a nice moment of inertia that's easy to calculate. Here we have a slice of PVC, which once again is a cylinder. I don't know, we'll use a thin-walled cylinder, I suppose, approximation for that, and we can calculate separately the moment of inertia for that. And we also have, there's three small bolts holding this together. You could treat those as small cylinders and calculate the moment of inertia for each one of those. And you could add all those pieces together to come up with a total moment of inertia for this non-homogeneous object. So here's our goal. So everybody will be assigned an object. You'll work in. And what you'll need to do is, first of all, calculate the moment of inertia for your particular object. And then what you'll do is predict the acceleration down the ramp. And I would do this general solution in terms of a general homogeneous rolling object rather than a specific one. In other words, use I equals k mr squared rather than 1/2 mr squared or 2/5 mr squared or something like that. And then let's run an experiment and collect some information about it, and then take a look at the results and conclusions and see if it actually matches our expectations. So the first thing you'll need to do is choose an object, and we actually have 11 different objects to use. Abraham's exercise wheel I'll do as an example. So what we'll do is we'll have everybody take a look at the blue Matchbox car and use that maybe as our control for our experiment. And the big question about this Matchbox car is the Matchbox car is rolling on wheels, and even these tiny little very, very, very lightweight wheels, they do have a moment of inertia. And as mass and radius don't appear to matter, will this be slowed down significantly because of that moment of inertia? So the question is, how do we design the experiment to collect our data? The method I ended up using, just to make a quick data analysis that we could all pull off as a group, was a videotape showing each one of these objects rolling down in slow motion. The question is that the best method to collect this data? And that's something you can talk about in your results and conclusion. Here's just going back to our rolling car question. I was treating this, and we did in the past, as an object sliding down a ramp with no friction, not taking into account any of the moment of inertia of the wheels. And even though these are tiny little wheels, all four wheels only have a mass of 1.65 grams, and we found that mass didn't seem to matter, nor did the radius. However, moment of inertia is moment of inertia is moment of inertia, and these do have moment of inertia, and that should slow down this car. So did that actually happen? So I carefully measured and massed all the objects for you, and here's the basic information that you're going to be using. And all these objects will be assigned to different groups. So before we run an experiment, you should actually use the theory that we've worked out for moment of inertia and using torques and energy to predict what the acceleration and final velocity of the rolling object would be down a ramp. Now, I would recommend, rather than using your selected object to do this, I would use a general solution with some object of mass m and radius r, and use it using a homogeneous object, because all of your objects are homogeneous. So whether it's a solid sphere, a hollow sphere, a solid cylinder, a hoop, etc. Use I equals k mr squared rather than 1 mr squared or 1/2 mr squared or 2/5 mr squared or 1/3 mr squared, whatever, and come up with a general solution for your acceleration velocity with respect to k, m, r, etc. I'm going to go through this process with Abraham's exercise wheel. This is a non-homogeneous object, so I'm going to come up with a general solution for a non-homogeneous object, and then I'll plug in the exact numbers for this that I calculated. And here are the numbers that you did for a homework assignment. And we disassembled this and took measurements. Of course, I'm a little bit suspicious about this 36 because I didn't put a decimal point after it, but let's assume it's 36.0, and let's assume everything's to 3 significant digits here. So our goal here is to find the moment of inertia for this non-homogeneous object. And as I mentioned before, all we're going to do is disassemble the object in essence and work out the moment of inertia for each one of these parts. And some of them we can use doubling or quadrupling. We have 2 plates on the outer edge, for example, and those we can just double, and we've got 4 bolts that are off center here, and we can use the parallel axis theorem to take care of that off centered bit, and we can just multiply our result by 4. After we've found the moment of inertia around its center of mass, which I have marked here, I'll ask you to take a look at the moment of inertia shifted out to the edge, and once again all we have to do is apply the very simple to use parallel axis theorem to come up with that alternate moment of inertia for along the edge. So here's a general form I asked you to fill out, and I'm going to go through it now. I'll break things down. So the 2 large acrylic discs, those are homogeneous with a k equals 1/2, so I equals 1/2 mr squared. And I had to do a little bit of math to figure out what the mass of those 2 discs was. And the radius is just the diameter divided in half. And make sure we're using MKS units for all these things. We need meters and kilograms for these things, not centimeters or grams. Plug it into our formula, and note our units for moment of inertia are kilogram meter squared. So 0.0229 kilogram meter squared. That's our moment of inertia. Also, you could informally call that a rotational mass, but don't tell anybody on the AP exam about that term because they won't know what that means. And you'll notice, compared to our 1.4 kilograms, seems to be a pretty small number. So is this significant or not? Well, we'll see. Now, for the PVC cylinder, I'm going to treat that as a thin-walled object, so all the mass is out at the edge, like our brass hoop. And we're going to use k equals 1 for that. I equals 1 mr squared. So taking its mass and its radius, and we calculate that to be 0.000908. You see that's much, much smaller than this. So the final set of objects we need to consider are the 4 bolts. And those are small cylinders. So we'll use those k equals 1/2 for that. And then what we'll do is we'll use the parallel axis theorem to shift that out to the edge. Now the question is, if these are so small, could you really consider them as a point object, just shift it out to D and use k equals mr squared? And you could probably do that, but I'm going to use this methodology. And if you did the other calculation, you'd probably find it wouldn't be a significant difference. So the mass of each bolt is about 9 grams each. The radius of each is about 3 millimeters. So they're about 6 millimeters across in diameter. And if we actually take our moment of inertia using parallel axis theorem and plug in, we find that this is our result. And once again, it was as small as our PVC cylinder was in terms of relative to our acrylic discs. These are even smaller yet. If we add all this up, we find out it's 0.0239 kilogram meters squared. And just to show you once again, could we have ignored the PVC cylinder and the bolts? The bolts, certainly. They're way too small. They didn't really affect our moment of inertia at all, out to 3 significant digits at least. And the PVC cylinder had a small effect overall, down in the 1 or 2% level. So we probably could have ignored that and gone with our large acrylic disc. Of course, you don't know these things until you've calculated them and get some experience doing this. So here's a summary of the results. So here's our moment of inertia around the center of mass, which is in the center of our exercise wheel. Well, what if we treat the object as rotating around its bottom edge as it rolls around a table? And we did this, if you think back, when we looked at the ant on the bicycle wheel. As a bicycle wheel rolls, you could actually envision the wheel rotating around a point touching the road, and you would actually move the rotational point down to the bottom. And I'm doing that here. And what we found out is when I shifted down to the bottom using my parallel axis theorem and adding md squared with the radius of the wheel and the mass of the object, we find out that our new moment of inertia at that point, if we decide to use that for some reason, is 0.0795 kilogram meters squared, which is a much larger number. You'll notice it's almost 4 times bigger.